Dear colleagues, dear academic community member of the Babeş-Bolyai University, honored audience, my name is Lucian Baia. I'm professor at the Faculty of Physics of the Babeş-Bolyai University, and I welcome everyone to a new presentation from the series of conferences organized with the Studium Generale program of the STAR Institute. As we all know, Studium Generale is a platform where research is presented and interdisciplinary discussions can occur between teachers, researchers, and students. Today, we will have a presentation on the interaction of semiconductor nanoparticles with the environment, an early alarm towards the scientific community, which will be given by our colleague Zsolt Pap, a newly appointed lecturer in the Department of Biology and Ecology, Hungarian line, at the Faculty of Biology and Geology of Babeş-Bolyai University. Zsolt will highlight key aspects of the environmental impact of technological developments and the use of nanoparticles, which are widely used today. Thus, as a result of the deterioration of the technological tools and considering that nanoparticles are incorporated into technology, they all eventually become waste. As a result, it is almost inevitable for these particles to end up in nature, where they can have a significant impact on the living organisms. Before giving the floor to Zsolt to discuss this topic, I would like to say a few words about him. He graduated from the Faculty of Chemistry and Chemical Engineering at the Babeş-Bolyai University with a degree in Chemical Engineering. Zsolt then earned a Master of Science in Applied Electrochemistry from the same faculty and obtained in 2012 a PhD in Environmental Sciences from both the University of Szeged and Babeş-Bolyai University. During this time, since completing this PhD, Zsolt has had a prolific scientific career, publishing numerous high-value scientific results, leading numerous research projects, supervising several doctoral theses, and being a member of the teaching staff at the Faculty of Biology and Geography since 2013. He has also been an Associate Research Fellow at the Interdisciplinary Institute on Bio-Nanosciences since 2014 and a Research Fellow in the Department of Applied and Environmental Chemistry at the Institute of Chemistry, University of Szeged since 2020. Also since 2019, is a scientific researcher at STAR UBB. Before inviting Zsolt to introduce us to this fascinating topic related to the interaction of semiconductor nanoparticles with the environment, I would like to remind our online audience that they can submit their questions via the university YouTube channel, where the conference is being streamed live. At the end of the presentation, I will gather the questions and I will address them to our guest. With that, I would like to thank Zsolt very much for accepting the invitation to speak today, and we look forward to see his presentation.
Okay, thank you very much for the introduction. You said that I should take the floor, but I'm taking the couch, so I think it's better to say that rather than the floor. So let's try to focus on today's presentation topic. Professor Baia highlighted quite well that we are in the verge of different kind of technological evolutions, which means that we have a lot of technologies and we have a lot of materials in our hands which are nowadays treated as given without any problems. So this is in fact the title of our presentation, which we try to go through, that we try to analyze what nanoparticles are doing in the environment. Can we have environmentally friendly nanoparticles? And what is important towards the scientific community to analyze these aspects. So again, then let's dive into the topic. So this is a short presentation first of the outline of this short lecture. So we will talk about a little bit about nanostructures. We will go through a little bit about our today's technologically driven life. We will also have an aspect regarding the advantages of new technologies, and also we try to look, let's say, the back of the shadows, let's say behind the curtains, what we can talk about relating nanoparticles. Later on, let's try to focus on the area which tries to uncover the backlashes or the, let's say, bottlenecks of nanotechnology. And more or less, we will try also to focus on different technologies, especially on solar cell technologies, which are quite supported also by the European Union and also by the world. But we have also here, let's say, a very gray area which nanotechnology brings to this green technology on the back. And also we will draw some conclusions together at the end of this presentation to see if, let's say, nanoparticles are bad or good, or both of them. So let's try to immerse ourselves first in the world of nanoparticles. Let's say that nanotechnology is not invented by us researchers, so it's invented more or less by nature. So as you can see here, we have, let's say, different size values which we, as we go through the nature, we can surely see. So we also know about, let's say, ants, which are like millimeter size. We know about ash, if it's burnt something, which are like micrometer size. But we can go through the levels of blood cells, which are less than 10 micrometers, or even go to the, let's say, the level or the world of the cells, which are at the level of nanometers, which is in fact the DNA, let's say, which is nearly half of nanometer. But parallelly, we can go to the discussion of, let's say, man-made nanotechnology comparably to the natural nanotechnology, which means that we know that very well know the pin or the hairpin or any kind of pins which sometimes we hurt ourselves. They are like in the zone of the micrometer size or millimeter size. But we now invent nowadays also nanoelectronics. You can synthesize or you can prepare nanogears, so, or in microgears. You can create nanoelectronics with nano-sized wires, or even print atomic level devices. All of that, which means that we can together imitate nature in more or less, let's say. However, there is a special things rather than one thing about nanotechnology and nanoparticles. And that is, usually nanoparticles are considered the very, very small version of the bulk, let's say, particles which we can see with our eyes. But in fact, they have a special property, which means that as we go from size to size, let's say from a bigger cube with a three-sided, as we go to the one-sided cube, which is 1/64 of the original cube, we can see that the ratio of the squares which are on the surface reported to the squares which are not on the surface, as we are going down with the size, the amount of surface squares increases. It can be even more visually presented if we have a cube which we want to split. Or you can imagine an apple if you want to have something more visual rather than a cube. If you cut let's say a cube in two, you will have a bigger surface. As you cut again the cube which was obtained from that one, you have an even bigger surface. So as you go to, you are going through the nanometer size, you will have a 1 centimeter cube. If you make it nanometer size cube, you will have 60 million square centimeters as surface. So the main issue and the main properties of the nanomaterials are issuing from the specific surface qualities which are totally different than the original nanoparticle or the original particles which we can see with our eyes. So this means that nanoparticles have specific surface properties, and that is why a lot of researchers are focusing on obtaining them, because they have their advantages at different technological applications. So let's say how we researchers are facing this problem. So first of all, when I was a PhD student, of course, and nowadays also, we try to satisfy the commercial need for nanoparticles, because we have a lot of technologies, we want to develop a lot of new things. So that is why we try to make these nanoparticles safe as possible, of course. We can make them inert to the environment as possible to not cause any harm. We want to make them recyclable, and more or less, of course, this is the main reason to doing that, is that we want to make them our lives better. But there is a major problem. Usually when we do something new, we forget what it does, in fact, to the environment. So we forget about issues, the following issues, let's say. Are they really safe? Because we are sometimes focusing just on the application. We are not thinking backwards. And after that, what is happening to them? What if they arrive at the city dump, let's say, as a few particles? Or what if they are driven by air? We don't know. What is happening if they have some side effects, which in fact can make our lives not better, but in some cases even worse? So as a researcher, I think we had the issue of scratching our head, if you want to be correct, to investigate what are the backlashes of nanotechnology and nanoparticles generally. But researchers, as I don't know if you all know, but researchers are pretty sure know that we are living from papers and manuscripts and publications, so we are let's say under a lot of pressure. So as the time, let's say from early researchers, they have just the task of publishing their new results. Now you have to be more strict, you have to be more effective, and you have to publish more and more and more, which means that you have less and less and less time to think about and to evaluate your results. So how are we gonna treat them? Because nanotechnology is not bad in nature, let's say. Because nanotechnology has a lot of application which, let's say, it made easy for us. So we have, of course, solar cells, we have electronics, we have high-speed computers from nanoelectronics, we have sensors, of course, for a lot of devices, and these are made from these very beautiful nanoparticles. But of course, sometimes researchers are a little bit crazy and make something like this. So I think also researchers deserve some fun when we are doing some kind of nanoparticle stuff. Rather, let's try to consider from every aspect the issue of nanoparticles. So let's try to construct the road of nanoparticles from the start until the end. From the start, we have to synthesize these nanoparticles, which is logical because nature does not make nanoparticles. Okay, I have to make a short outcome here that in nature there are nanoparticles, but not controlled nanoparticles. I think that's the correct word for them. After the synthesis, we have the application like solar cells, sensors, which we discussed earlier. And of course, we have when the application expires, like your phone is broken, your device is not functional anymore, you have the waste, of course, which is the end product of its lifetime. And each of them has, let's say, a more specific backlash of it. Let's say, when you are starting the synthesis, you have a lot of materials and processes which they consume energy and may have carbon footprint. If you go by the application, there is difference how you apply those nanomaterials. You apply it in a technology which is beneficial, or you apply in a technology which more or less will result in a negative impact. And there is the last part, the nature of the waste, which is obtained from this technological sequence. So there are a lot of issues which have to be considered when we are talking about nanotechnologies. So as a partial material scientist, I am, let's say, with this face, I'm not so happy about it. So I ask the question, also for the audience, of course, but also for us, that do environmentally friendly nanoparticles even exist? If we put the question and formulate it like this, I think we can give an answer when we finish our presentation, more or less. So I want to make a short glimpse, I want to present a short glimpse about the synthesis of a nanoparticle. So it looks like this, with a lot of processes, a lot of materials. So just a simple synthesis of titanium dioxide, which is a very known material. It is also what was a food adherent, not long anymore. It requires several steps. And all of these steps, which you see here, consume energy, consumes chemicals, and of course, it has its own byproducts. So it means even the starting point of nanoparticle synthesis has to do with the environment. And let's talk about now a little bit regarding the end. The end life, the product arrives somewhere, because not all the waste which is related to nanoparticles like electronics are treated as electronic waste, because usually people, when you talk about nanotechnology, people are thinking, okay, everything which works with electricity is related to nanotechnology, but that's not true. There are a lot of applications of nanotechnology which does not have anything to do with electric circuits. So that is why nanoparticles, in fact, are now getting in our environment slowly due to the degradation of different kind of products which we already put it on the market. So we have, in fact, three ways of nanomaterial propagation. We have, of course, air as in form of dust, in soils due to different kind of waste management processes, and of course we have the matrix, the water, which can carry these particles further. And of course these three major matrices can be combined, which means that they are interacting constantly with each other, meaning that water is always in contact with the soil, air with soil, and air with water, so we cannot ignore their direct relationship. This means that we have to monitor at different levels. We have to monitor the environmental changes. We have to monitor the interaction of these particles effectively with the environment. And we have to monitor also the changes which occurs in the nanoparticles. Why am I putting this in red? This is quite an important aspect, because for a product, you can say that this has nothing to do, this is not toxic, you can analyze it, you can use it anytime. But maybe this nanoparticle suffers a transformation in the environment which will make it toxic later. So that is why I'm subjecting this issue in red, because sometimes it could happen that a non-toxic particle can be transformed into a toxic one. So this is our main reason that we try to focus on each of these issues while talking about this, let's say, more or less more interesting reason to do this kind of research. The main research area, if I'm talking about research now, is the nano-ecotoxicology, which is focusing on the matter. Why? This is the interdisciplinary area which has nanotechnology in it, like means it has material scientists like myself. It has biologists, ecologists, which are expert in the analysis of different kind of living organisms, their biology, their behavior, their ecology, and so on. And you need desperate of toxicologists who knew the exact mechanism of toxicity of these nanomaterials. So when you are talking about, in fact, a negative or let's say even positive effect of a nanoparticle, you need a nano-ecotoxicologist to have it in your house, to investigate if your, let's say, particles which you are using for your technology is safe or not. Classical ecotoxicology, which focuses, is already present for, I think, nearly 20 years ago. So it is not that young research area, but is the most debated one due to the conflict between the commercial side and the academic side. Because sometimes, as you can see here, this is just one example of many. The researcher, it doesn't really matter who, investigated the negative effects of silver and gold nanoparticles, and they investigated on a specific type of fish, and it was found that they modify the evolution or their body type, different kind of evolution rates, and causing serious deformation. And the particle, those manufacturers who provided these particles were not keen that this publication appeared in the public due to the fact that it make them in a negative light due to their product causing an ecotoxicological effect. So let's go back a little bit and let's try to discuss about what drives nanoecotoxicology, what is the driving force of this research area. So in fact, it's really simple, as already stated in the presentation, that nanotechnology is pressed to give new products daily. So as you see here, this is a graph, more or less a recent simulation, which tells that the market of nanoparticles generally, it's constantly increasing. Right now, it's about $5,000 billion nowadays, which will arrive at $387 billion, which means it will have a significant increase in the next 10 years. So it means that nanoecotoxicologists will have a lot of things to do. And just to make it in a more practical concept, in 2022, this amount of money, like $99.24 billion, represented 11 million tons of nanoparticles. So you can imagine if you multiply 11 million tons with nearly 30. So it is a lot of nanoparticles. It's larger than any kind of other products manufactured nowadays in any industrial area. So this interesting situation causes that a so-called greenwashing of the nanotechnology occurs. And I made an interesting experiment yesterday that I asked artificial intelligence, which is now quite actual today, that what are the major applications of nanotechnology. The first was one immediately nanostructured solar cells. And interestingly, all the other applications are quite crucial for each of our life segments. So you can see nanostructured solar cells to have electricity just with the help of the sun. You can have hydrogen production. Of course, everybody heard of hydrogen-driven cells for cars. Or batteries, which are now quite important for electric cars. Also, we know the issues with the different kind of batteries recharging and discharge issues and reusability issues. And after that, the second one was environmental remediation. The fact that we are trying to prove that not all the cases we are having environmental remediation, but a negative effect. So sometimes they use nanofilters, water purification, air purification, even they have sometimes used to clean up even oil spills. So if we regard these technologies, we can see that everyone has a great amount of funding in it. Like society invests a great amount of deal in it because it solves some of our major problems. However, it is applied, let's say, in a hasted way without looking a little bit in more detail with the possible effects regarding our environment. And wanted to focus a little bit on solar cells. Why everybody wants to obtain solar cell related materials, and why do we want solar cells on rooftops? It's very easy because, as we said, that we have renewable energy. It reduces electricity bills. Of course, who doesn't want something like that? It is environmentally friendly, theoretically. We will see that is not that simple. It is a low maintenance, like you don't have to invest a lot of money. It takes you 25, 30 years of life, which is quite good. And of course, a lot of technological advancements are going in this field, which means that even more efficient solar cells are appear nearly yearly. And that is even true because we have a race for solar performance. As the National Renewable Energy Laboratory from the United States every year monitorizes the evolution of the solar cell efficiency, we can see that we have quite an intensive race, and currently we are at 48% of photocurrent or let's say for cell efficiency, which is quite good. But if you look closely, this nearly 50% of efficiency is achieved by materials like gallium arsenide. So I think everybody with the general knowledge of general chemistry if you say arsenic is not a friendly word, we can agree on that issue. And you don't see a lot of commercial solar cells containing gallium arsenide. It is, of course, to several reasons, due to the stability and due to the development type of issue now. But otherwise, all the solar cells have something specific in their structure which may have an impact on nature. What is the state of solar cell reusability? The important thing is that solar cells are a composite type of waste, which means you cannot treat them equally like you usually do with any kind of electronic waste, because it contains glass, it contains plastic, it contains the optical active layer, it contains electric circuits, it contains also a lot of type of materials, and its, let's say, efficient type of treatment is not so obvious. And this is quite a problem, and this can be seen from the market analysis values. If you go through the market of the solar cells, generally speaking, let's say perovskite-based solar cells, perovskites, we will talk about them later, are new materials which are quite efficient for solar cells. And we now generally have at 2023 around $64 million market, which will grow nearly to $1.7 billion in 2032. And the total market will have a similar growth, while the solar cell recycling will not have the same amount of growth as the solar cell development, which means that sorry, we will have new materials for solar cells, but we will get behind in analyzing the impact of these materials on our, let's say, on nature. So let's ask again the questions as 4 slides or 7 slides ago. What is the degree of recycling of our solar cells? Can we do it 100% or at least 50%? What are the valuable components? Of course, there are a lot of valuable components like the perovskite itself or the active layer itself. And what is the price of recycling? We all well know that for batteries, by example, the recycling price is not as high as their synthesis price. So it is not that easy. And also, we may tend to suffer the pesticide syndrome. What is the pesticide syndrome? It is not a common word, but we know that in the early 90s, a lot of pesticides were developed to have an increase in different kind of crops also throughout the world. And DDT was developed. Now, if you look at an advertisement board from the 40s, it looked like this. So DDT is good for me. Now, if you go with this type of, let's say, advertisement, you will not get accepted, because this is now, we know that this is not so good as it says in the development board, which means that we may be doing the same in the case of nanoparticles as we done for DDT, which means that we may have negative effects which we don't discover in time, and later on it will be too late to do some action to get back the negative effects for this kind of materials. So there are also quite different examples when biologists, in fact, try to get in, let's say, in a war with specific manufacturers with pesticides, in fact. There is Dr. Tyron Hayes from Berkeley, who in fact had a lawsuit with atrazine manufacturer Syngenta, and he didn't manage to get his point through. Even he had scientific evidence that atrazine in a specific concentration is quite, let's say, not, is quite negative, had quite negative effects on different kind of species where he investigated. And interestingly, his research was covering nearly all. He gathered samples from different kind of water environment, from agricultural fields, from water, river waters, and he had in fact a solid evidence that atrazine is not human health friendly material, and also not for the environment. So let's not have that pesticide syndrome if it's possible. So that is why in the presentation which we follow, we try to highlight very similar aspects, not the drastic ones, but maybe we can think about how to analyze or how to approach these materials. So perovskites generally, which are used now in solar cells, there are, let's say, numerous. So we cannot go through all of the material types. I just selected 5 or 6 type of perovskites because they have efficient charge separation when they are used as optical active layers. They are pretty good in visible light excitation, so it means they can utilize visible light quite well, which is important for solar cells. And sometimes not just for solar cells, also for other type of applications like strontium titanate can be used for energetic applications, which is not solar cell, like let's say for CO2 reduction, for hydrogen production, but not by solar light-driven versions. And of course, the major question arises, what is the stability of these materials, generally speaking? So I'm taking now 2 examples specifically, namely cesium lead iodide and cesium lead bromide, which are some of the 2 most promising perovskites. Of course, there are others which are quite efficient in this matter. So I'm not entering in details. Most importantly, that we obtain these materials with different kind of precursors, as I have stated previously in our slides. And of course, we obtain these materials. You have a photo about it here. And this is an electron microscopic picture of them showing their current state. So we have the nanoparticles, and we wanted to analyze first if they are what we are thinking they are. So we have taken some other measurements. I won't bore you with excessive details. The most important thing is we did X-ray diffraction. The takeaway note is that all the reflections which you see here are in the same place, which means that the material which we have obtained is indeed cesium lead bromide, or in the other case, cesium lead iodide. So this was the purpose of the first investigation. The second one was about an optical analysis, which means that we wanted to find out if their color is appropriate for the visible light absorption. And indeed, for the cesium lead bromide, these values for the excitability of these materials, for the iodide and for the bromide, were perfect. So other details are not important regarding today's presentation. However, what we did, in fact, that we did a so-called soil extract, which in fact is a very easy thing to do. You can take a cup of soil anytime from your garden, put it somewhere which water goes through, and make an extract of that soil. So all the components which are in the soil and are water soluble, it can be retained in the form of soil extract. So we have taken 2 types of soils, one slowly acidic and one basic soil. And we did a very simple experiment. We just take these materials which were for solar cells, optical part, and put them in a suspension. We made it, let's say, a suspension or a tea of some kind of sorts from these materials. And after a specific time, we took 2 times, but that's not important, 4 on 72 hours, and we analyzed the composition of these materials. And we have found that all the compounds, or at least all the solutions in which we have investigated, had lead in it, which is quite not a beneficial thing to have. Usually lead is quite toxic and it is a heavy metal. And think about it, that these are 4 and 72 hours investigations. More or less, if we go back and see the electron microscopic figures, we will see that this was the original nanoparticles, and after entering in contact with the soil extract. If you still have a little bit problem imagining the soil extract, you can imagine like a soil which is irrigated by effectively the rain. So a soil extract can be in fact rain having an interaction with your soil. So if these nanoparticles are in the soil in any kind of concentration and it is raining, then these materials will slowly transform in something else. And this was also supported by our analysis of the color of these materials. These small pictures, I don't know how visible are, below is the original color of the powders, and the other ones are after having the interaction with the soil extracts, which means that effectively having the nanoparticles in soil and just having rain, nothing more, it gives you a transformation of any kind. We will enter in detail a little bit later. And also we have to say that these materials are not usually so stable under water, under moisture, so this is a known fact, but usually this is a more hidden fact regarding the analysis of these materials. But you don't know what will happen if it's a little bit a longer exposure or on other type of perovskites. So it is mandatory that we have to investigate what is happening to these materials just in fact in the soil. We did after that, being interested what we observed in the soil experiments, we now made a plant, a phytotoxicological experiment in which we had rapeseed as a substrate, in which we tried to find out if it restrains, the presence of these perovskites restrains their growth. This theoretically, if they don't have anything to do, all the plants will go, let's say, will grow in the same way. Interestingly, we have found that this is the reference, which means that it did not contain any kind of perovskites, but any kind of other materials which we have used for our analysis, it inhibited the growth of the rapeseed, which means that something must be happening to these materials that it inhibits the growth of these plants. And also, we have found an interesting evidence that these materials are causing direct stress to these plants. You can see very faintly that some of the small plants are having a reddish type of hue, which means that usually rapeseed under stress, any kind of stress, it can be oxidative stress or it can be any kind of pollution, it results in a coloring or decoloring of the leaves. And we have observed that. So we are now in the verge to further investigate what is really happening. What is the mechanism of toxicity? What is the dosage which we can analyze or to have an effect on the plants, and how is the interaction going? So let's say encouraged by this, we plan next studies to expand these kind of investigations, like microbiological studies, which we already started, hydrobiological studies to see, in fact, these perovskite particles, what are doing in water, in fact. And also, we have started to focus on behavioral study, because toxicology is not always like if you die or not, or the investigated entity, biological entity dies or not. Toxicology is also impact of behavior or some kind of difference between the original status of life and the new one after the impact with the nanoparticles. And of course, if we are lucky, we can also have human toxicology studies, and also the establishment of a database to have all the particles listed in more or less in a standard way characterized in ecotoxicological tests. And also I want to go back with the thinking a little bit towards the behavioral study, because sometimes a quite simple experiment, or at least basic, or even, let's say, quite out of the box experiment can prove something very important. So now I'm changing a little bit the topic. So as I said, perovskites are one class of materials which are used in solar cells, but there are other ones like titanium dioxide, which is a vast, this is the, let's say, the heavyweight of nanomaterials, which means that it is obtained in tremendous amounts. And we did the same. We just wanted to have some interesting hydrogen production experiments with these materials. And of course, for that, we needed titanium dioxide, which is this commercial product, which is named Evonik Aeroxide P25. And we had two noble metals to be associated with, because that is needed for the process. And of course, We did the investigation, we had pretty good results, but we had a suspicion, accidentally of course, usually sometimes accidents happen, but this was a good way. One of my colleagues who investigated this caught her attention that the conductivity of the solution increased drastically and also the pH. Nothing more happened, but it increased the solutions in which we avert the conductivity, which means that some kind of ionic content or conductivity increasing content was slowly leaking into the water. And also this induced a pH change. So we had the suspicion that something is not right. And we already were in the starting of the ecotoxicological experiments, and we thought about, okay, if you have a pH change, this means that some of the living entities in our worlds have quite a high sensibility regarding the pH. Even humans ourselves, let's say there are some kind of pH levels which we tolerate, even in our blood or in our stomach or in every kind of organism which we have. There is a pH value or a pH interval in which it functions properly. So this is the same in case of different kind of species. Some of them have nearly no problems having a wide pH range changes, like bacteria. They can be from very acidic to very basic without any problems. But as we go to different kind of species like plants and algae, they're a little bit more sensitive. But fish, maybe even trout or the mayfly or even snails, their pH tolerance is extremely low, which means that if you change by, let's say, half of pH unit or a full pH unit, the pH of the water, their environment is not suitable for living from their perspective. From our perspective, of course, a change in half of pH by drinking water, it does not count. But for them, because it's a living media, it's sure it's an impact. So we just take these powders. We used an ecotoxicological reference entity with lemna minor. So this is a very resistant species, so we take nearly everything. It is usually present in our homemade aquariums, so you cannot rid of them. So if you have excess, please send to us. Of course, there is a specific growth media associated with it, and we irradiated with a UVA because these materials are activated through UVA. And we did the lake approach. Lake approach means that we just put the powders, we let them sink, and just natural convective forces are the ones that are making the mixing of the whole suspension. And interestingly, so it will be a surprise that we didn't observe any negative effects. So we were happy, more or less. But what we observed that even for a growth media, which is simulated, in fact, of a natural media, but a standard, we observed pH changes again, conductivity changes, and by a great amount. You can see here in this 3D graph that from the starting point, which is the pH of 6.5, which is the official growth media, standardized growth media pH, after 7 days, it went up with 1.5 pH units, 1.2, 1.5 pH units. So this is much. Considering that the amount of the powders which we used were in the order of milligrams. So this means that just by having nanoparticles in water, you can have pH changes. Okay, you won't put in sacks or kilograms in a lake, that's a fact. But locally, it can change the pH. And in case of lakes, where the water mobility is not that great, as in case of rivers, it can be a problem. And also, we observed the changes quite significantly. This is the base pH of 6.7 in the base. And all the nanomaterials which we have used increase the pH significantly. So this means even that the lemna minor reference ecotoxicological entity did not have any negative effects on its growth because it's quite resistant, but it suffered the pH change. And of course, that pH change cannot be related with the growth of these entities, as we also monitor the reference experiment where this growth just was 0.2 units. So, as again, we try to focus on what is happening not just with the entity, biological entity, but also with the media. And again, we have the issue as scientists, as we have to hurry through the path of science. We have to have also just a one-point view world. Like you want to pursue a very good solar cell, then you go through that solar cell obtaining path as intensive as you want. So by going through that, we have to find about the interactions. As we have said, we have a quite complex mechanism in case of soil, mobilized nanoparticles, fixed nanoparticles, and of course, which I said to you that rain interaction with soils results in a soil extract. And of course, there is the other ionic species which have the interaction with these nanoparticles. And now, continuous interaction is of course the nature's main issue. So we did a very similar experiment as we did with the lamina minor, but this time we just did a very simple approach, like putting these materials in soil extracts and tested their photocatalytic performance, which is in fact a way of test their semiconductor properties. Everybody says that if nanoparticles are inert, they are inactivated in nature, but this was not the case. Let's say if this was the starting material, the dotted lines are for the particles which are in nature. So they were not inactivated at all. In some cases, we even registered an increase in semiconductive properties, not just a decrease. And in other case, of course, we also didn't observe any decrease in the semiconductive properties. So these materials are active in nature, so not deactivated. So then we did other interesting experiments with ants, a behavioral type of approach, which means that we gathered ants in a specific way. I won't enter in detail. The interesting thing is that we treated them with titanium dioxide on their surface. Why we did choose ants? Because they have extended network, they have complex interaction with the local environment, and everything which is happened to them are happening also to the environment. So it's a late or a domino type of effect. So if I can start this is my colleague here with the ant sources. So let's go a little bit further. What we did, we covered these ants, which we used as experimental subjects, with titanium dioxide. It should be known that these ants in the surface have the so-called cuticular hydrocarbons. It's like an identity card for them. And if that is changing, then they cannot reconnect with each other. So they are treated among them as strangers. And this is what this also have a 24 hours of cycling, which if you remove it in 24 hours, it is let's say regained. So we had two species of ants. We used specific experimental conditions using titanium dioxide. We irradiated them, and we observed their behavior. And also, of course, a lot of references were made just to emphasize the importance of the results. And after that, we did an analysis if we have the same cuticular hydrocarbon composition. So first, the behavior. We observed that the original behavior pattern with different kind of like grooming, feeding, mandibulate changing, biting, acidic type of interactions had a specific pattern. As we exchanged the ant which was sprayed with titanium dioxide, let's say this is the white one, this was sprayed, we had a change in interaction. As we sprayed the other one, we had another change in interaction. As we sprayed both of them, again another type of interaction changing. So this was only possible if the composition of these hydrocarbons changed. And that was the case. The black one, there are a lot of compounds, the name is not that important. Most important is that this is the original composition of the hydrocarbon profile of that specific ant, and the red is after the contact with nanoparticles. So you can see a variety of changes in their profile. So, in fact, that we can make by using these nanoparticles just change the behavior of ants. And of course, we analyzed a lot of particles, a lot of compounds, and we observed the same. So we can summarize something like this, that after the interaction with nanoparticles, our ends were like unidentifiable. So it means that we intervened in the social interactions in the environment. So we can ask the question if it has a direct interaction for other kind of social insects or communication devices. And of course, I want to, let's say, summarize it again, that what is the conclusion of what I try to present it here? I say the conclusion, in fact, is quite complicated, and with a simple summary, that we should have a waste or we should have a technology. I don't know. The most important answer is that you should not throw away your solar panels from your house, but you should ask for your manufacturer where the waste is going. So at least you can do that to be absolutely sure that maybe they are really utilizing your solar panels for something good. So thank you again for your attention, and thank you, my colleagues, for the great amount of work. I think I don't have enough slides to put all of my colleagues' work contributed to this beautiful work. And of course, if you have any questions, I'm more happy to answer it.
Yeah. Okay. Thank you very much, Zsolt, for this really interesting presentation. Listening to you, I realized that we must be getting desperate.
Like always.
Yeah. Okay. Okay, the talk is now open to questions and discussions. Just to check the chat. Yeah. Okay, we don't have any question on the chat, but if there are questions from the audience who is here, no, then I have two questions, actually, a short one and then maybe an opinion from you. Okay, the question is, so anyway, the very small particles, nanoparticles under, I know, 10 nanometers are toxic for humans. In the case of the solar cell or other technologies, maybe particles are a little bit higher. Okay, but the question is, you're a chemist at the background. Do you think it's possible by performing research focus on changing the surface, the chemistry of the surface, is possible to reduce the toxical character of the particle, of the nanoparticles?
Yeah, this is a very good question. In fact, it can be answered on, let's say, in two ways. We have the toxicity at elemental level, like in chemical level. If you have lead, you do not have any other options. There is lead there. And there is another situation where you don't talk about the chemistry of the material, you talk about the surface of the material, which was your question effectively. So let's go by the first, which is more simple than the second one. The first question is, you refer about the toxicity, if we can change it or make some surface modifications which can hinder the toxicity originating from the elemental type. And the elemental type can be lead, by example, or can be even cesium or other kind of metal ions which can accumulate in living organisms. So to hinder that, maybe you can cover that nanoparticle with different kind of protective layers. But the problem is again with these protective layers, that let's say you can put a silica coating or a core shell particle or some kind of approach, but if you make a core shell particle, then you cannot use it in solar cells because it's isolated from the rest of the particles. And let's say you manage to somehow develop a coating which does not interact with the electric part of the solar cell. Then you have the issue of the coating stability. And again, then you have to work about how the coating, if it resists. So you have the problem, when your element is toxic, the only way is or you reuse all your particles, or you protect them in such a way that the protective layer does not go away. But that's a huge challenge, and I think it would raise the prices extremely high. So that is why the second one is a little bit easier to go by, like surface modifications. And yes, you can do such surface modifications like by locally inducing. There are also some research papers who are treating this aspect to treat the surface to have a recrystallization into a different kind of, let's say if you have cesium, let's say lead iodide, then you can change maybe the crystal structure partially, which is not that unstable. But you have to be very careful during this synthesis because the crystallization, you cannot limit the depth of recrystallization. So it is also again a very hard test to do. So that is why the overall answer for this, yes, you can limit somehow, but then the application costs will, let's say, will take high rocket. And because we are talking about commercial applications, I think they won't do that. The people who are doing this kind of research, most probably they will change effectively all the material.
Okay. Actually, you passed the ball to me because the next question is actually I need your opinion regarding there is a competition between to make money and the human, the population health, let's say, this competition. How do you see in the future this competition, actually? Okay, you can ask also artificial intelligence.
Yeah, I can ask his opinion about, her opinion about it.
Yeah.
So this competition, I think, is always with 1 foot ahead by the, not with the health, by the technological development, is always with 1 foot ahead. Because if you look through the history of humanity, always when you invent a new technology, you will care about the effects later because you want first the benefits, always. So I think as in any kind of technology, also we will do some actions when the, let's say, the level of the problem will be critical. Otherwise, technology always wins.
Okay. In other words, you suggest that we'll win the first part.
Yeah.
Yeah. How exactly to make money?
Make money always wins.
Okay. At the end, I would like to thank you once again for the presentation and the discussions, and also thanks the members of the Babeş-Bolyai University community for joining us. And we look forward to seeing you at the future presentations of the program of the Star Institute, which are broadcast live from the Taylor's Bastion. All the best. Have a nice afternoon.
Have a nice afternoon, and thank you for your invitation again.
Yeah, welcome.